Good morning, my dear students. Today I will start the physical chemistry, that is 6th sem, Raman spectroscopy. The Raman spectroscope. This is for BSc final year students. So under that we will start what is called as Raman spectroscopy. So what is the Raman spectroscopy? So in the year 1928, a physicist what is called as Sir C.V. Raman. Sir C.V. Raman from Calcutta University, he observed what is called as a ray of monochromatic light. A ray of monochromatic light passes through a prism. So when a light passes incident upon the substance, like what is called as a solid or the liquid or the gaseous state is, so it splits up into the three different frequencies. It will be split up into three different frequencies. One will be having the frequency of incident light more than that of the light. So they will be called as anti-Stokes lines. And if the frequency of the light is lesser than that of incident light, they will be called as the Stokes lines. And the incident the light, the frequency of the incident light is equal to, that is the refracted the light that is called as a Rayleigh's line. That is called as a Rayleigh's line. Suppose. So today that is a topic is Raman spectralism. So this Raman spectra means either if you take what is called a solid or the liquid or the gaseous substances, if you pass a monochromatic light. So for example, I can take a substance of what is called as a gaseous substance. I will purchase. So I will choose the best one is a gaseous substances. So for this gas substance, I will pass a light. Of frequency nu is there. So it will be having the 4896 angstrom unit light is for example. So it passes through a substance. It will be passes through, that is a gaseous substance like carbon monoxide or carbon dioxide, whatever it may be. It forms one spectral line. Then it will be having the another one line, and this is the another spectral line. So this line will be having the nu is equal to, that is 3896 angstrom minute, and it will be having 5296 angstrom minute, and this is called as 4896 angstrom minute. So here the Raman will be observed that is the Raman spectroscopy will be having. So three types of the spectral lines is formed when it passes through a substance of a solid or the liquid or the gaseous is there. So the substance will be having, that is incident light, will be having the same frequency, the 4896 angstrom minute. This line is also will be having the same 4896 angstrom minute. So we will be called it as this line will be called as Rayleigh's line. This is called as a Rayleigh's line. Then second one is, so if the incident light will be having the frequency, so that is 4896 angstrom minute, and it will be having this light is the intensity of this light is 3896 angstrom minute. This line will be called it as the Stokes lines. You will be called it as Stokes lines. And Raman will be observed that is the another light, that is the intensity of that light is more than that of the intensity of the incident light is. So here it will be having 4896 angstrom minute, and it will be having the 5296 angstrom minute. Hence it will be called it as it is anti-Stokes lines. This is called as anti-Stokes lines. So this is anti-Stokes line, this is Stokes lines, and the third one is what is called as a Rayleigh's line. So that is called as a Rayleigh's line. So here the Stokes lines will be having, that is the higher frequency will be called as anti-Stokes lines, the lower frequency will be called as Stokes lines, and the same frequency will be called as Rayleigh's lines. It will be called as a Rayleigh's line. So either if you take any solids or the liquids or the gases, there will be the gases like carbon monoxide, carbon dioxide, or sulfur dioxide, they can get the three types of the spectral lines. One is the Rayleigh's line, second one is Stokes lines, third one is anti-Stokes lines. So that is Stokes lines means the lower the frequency of incident light, and the Rayleigh's line means will be having the incident the light. The ray of incident light is equal to, that is what is called as that is the same the light intensity, the 4896 angstrom minute. So these are Stokes lines and the anti-Stokes lines can be represented the diagram be called as the anti-Stokes lines. So here, this is a broad, the spectrum, the line will be like this. This is another one, a line will be like this. So this is what is called as. So this line will be called as nu I is equal to nu S. What is this nu I and nu S means? The ray of incident light is equal to the ray of a scattered light. Both will be having what intensity is the same. So here the one spectral line, this is the second spectral line, this is the third spectral line, and this is the fourth spectral line like this is there. So here the sum of the what is called as spectral lines will be like this is there. So these lines will be called as the nu I is greater than nu S. Nu I is greater than the nu S. So that is nu I is greater than nu S means the ray of incident light is the intensity is greater than the scatter light is there. So these lines will be called as the Stokes lines. These lines will be called as Stokes lines. Then here this one will be called as the anti-Stokes lines. The anti-Stokes lines means here what is called as nu I is less than nu S. So the nu I is less than the nu S means the incident light, that is the intensity of the incident light is lesser than that of the scattered light. So that is called as anti-Stokes lines. So the Raman will be observed that is Rayleigh's lines, the Stokes lines, and the Stokes lines. The next, so this is called as that is if delta nu is equal to the nu I minus nu S, nu I minus and nu S. So that is called as Raman shift or the Raman frequencies. The Raman shift or the Raman frequency. So what is the Raman shift or the Raman frequency means? The nu I minus nu S. The nu I minus nu S means, suppose for example, the nu I will be having that is 4,896 minus of nu S means 3,896. So that is equal to, it gives the 1,896 angstrom meter. So this frequency will be called as a Raman frequency or the Raman shift is. This is called as a Raman frequency or the Raman shift is. So now we will be called it as this is called as a Raman effect. The various observations are made by the Raman, hence it will be called as a Raman effect or it will be called as a Raman spectrometer. The Raman spectrometer. So now we can come across how to prove this one, what is called as this is the Rayleigh's line, the Stokes lines, and the anti-Stokes lines. Under the anti-Stokes, the lines. So now the expression of Rayleigh's lines, the Stokes lines, and anti-Stokes lines. So what is the Stokes lines? The first one is the Rayleigh's lines. Suppose the Rayleigh's line means we will be having this is a 1, this is second energy level, the third energy level, the fourth energy level, fifth energy level, and this is sixth energy level. So 1, 2, 3, 4, 5, and 6. So that is this is called as the n is equal to 1, that is energy level 1, this is n is equal to 2, this is n is equal to 3, this is n is equal to 4, n is equal to 5, and n is equal to 6. In the same way, if we take it, this is 1, 2, 3, 4, 5, and 6 energy levels, the same, the 1, 2, 3, 4, 5, and this is the 6s. In the same time, the 1, 2, 3, the 4, and this is 5, and this is the 6s. So why I can write all these? This is called as energy levels. These are all the energy levels are present in either the molecules or the liquids or the gases. So n is equal to 1 means a K shell, n is equal to 2 means L shell, n is equal to 3 means M shell, O shell, P shell, Q shell, like that. So here, how to explain that is the formation of the Rayleigh's lines as well as the Stokes lines and the anti-Stokes lines observed by the Raman effect. Observed by Raman. So that is if an electron will be present, in the first shell, that is K is equal to the n is equal to 1 is. It will present in the n is equal to 1 or n is equal to 1, it will be not needed. Suppose the if electron will be present in the what is called as the original level is n is equal to 3. If an electron will be present in the n is equal to 1. If you pass a monochromatic light, the substance will be contains electron. So that electron will be shifted. It will be excited to that is the higher energy level n is equal to 6. The n is equal to 6 is so n is equal to 6. So here the excited electron in the higher energy level n is equal to 6 is not stable. It is unstable in the higher energy level because the energy of the electron is less than that of energy of this 6 energy level. The energy of the 6 energy level, and this electron jumped to the higher energy that is here. So immediately it will be jump back to the same original level. The n is equal to 3. The n is equal to 3. So this is called as a Raleigh's line. This is called as a Raleigh's line. This is called as a Raleigh's line. Then if the electron will be present in the same that is a 6 energy level, it will be jumped to. It will be jumped to that is what is called as a 4th energy level. It will be present in the 4th energy level. So that it will be called as that is a Stokes lines. That is called as Stokes lines. This is called as formation of Stokes lines. And if the electron will be present in the what is called as 6 energy level, so it will be it is present at 6 energy level, and it will be immediately jump back to the second energy level. So this is called as the anti-Stokes lines. This is called as the anti-Stokes lines. So how it forms either in the molecules of the solids or the liquids or the gases. So it will be having the different energy levels. So that the different energy levels, if a molecule of what is called a solid or the liquid or the gases, it will be contains. Suppose if you take only one electron. So one or any more electrons. So for this electron, the electron present in energy level n is equal to 3 means. So once if you pass a monochromatic light, so this electron will be excited or it will be jumped to the n is equal to 6 electron. The 6 energy level is. So this higher energy level n is equal to 6 is that is energy of 6. This energy level of n is equal to 6 is more than that of energy of this electron is. So that's why this electron, the excited electron, is unstable in the higher energy level. Immediately it will be jump back to the same original level. So during jumping from the higher to the lower energy level, so this energy, it will be called as a Raleigh's line. This is called as a Raleigh's line. Means the previous absorbing energy will be liberated in the form of a spectral lines. So that line will be called as the Raleigh's spectral line. The Raleigh's spectral line. Then second one is if an electron is excited from the 3rd energy level to the 6th energy level, so this excited electron, it will be jump back to the 4th energy level. It will be jump back to a 4th energy level. So this forms what is called the Stokes lines. The Stokes lines means the energy of the electron that is lesser than that of the incident light. This light will be called as the Stokes lines. Okay. Then what is called as the last one, in the 6th energy level, if the electron is present, the excited electron, that electron will be jumped to that is n is equal to 6 to the n is equal to 2nd energy level. So this energy liberated in the form of spectral line. So these spectra will be called as anti-Stokes lines. They will be called as anti-Stokes lines. Means the energy of the scattered light is greater than that of the energy of the incident light. The energy of the incident light. So this is all about what is called as Raman spectroscopy. Then in this Raman spectroscopy, next you can come across what is called as the rotational spectra and vibration spectra of Raman spectroscopy. Rotational spectra and vibration spectra of Raman spectroscopy. So here this is called as that is a pure rotational Raman spectra. A pure rotational Raman spectra for a diatomic molecules. So what is a pure rotational Raman spectra for a diatomic molecules? So that's a pure Raman spectra. A pure Raman spectra will be having a delta J is equal to 0, plus or minus 2. 0, plus or minus 2. So here 0 is equal to delta J is equal to 0, plus or minus 2 is. So now this can the pure rotational spectrum, that is what is called as the Raman spectrum, can be explained like this is that. So at the center there will be an what is called as this is the line. At the center this is called as a delta J is equal to 0. So this is called as a Rayleigh's line, and then next it will be called as a 6b, the energy gap. This is a 4b, this is a 4b, this is 4b, this is 4b, and this is a 4b. 4b. So in this the line delta J is equal to a minus 2 is that, and then here this side is also the same, that is a 6b, this is a 4b, this is 4b, this is also a 4b, 4b, and this is also a 4b. So we will be having this spectrum line. This is what is called as delta J is equal to a plus 2. 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 So this is a 1. So these lines will be called as Stokes lines, and these lines will be called as the anti-Stokes lines. Anti-Stokes lines. So that is here. What is the Stokes and anti-Stokes lines means? If delta J is equal to 0, plus or minus 2. Delta J is equal to 0, plus or minus 2 is. So here, what is this Raman spectra of diatomic molecules? If delta J is equal to 0 means that is what is called as Rayleigh's lines. If delta J is equal to minus 2, that is called as Stokes lines. If delta J is equal to a plus 2, it will be called as anti-Stokes lines. It will be called as the anti-Stokes lines. So that is energy of that is rotational spectra. Rotation level in terms of the wave numbers will be given by, that is mu mod is equal to Bj into Fj plus 1. Bj into Fj plus 1. So now I can call it as, this is equation number 1. So this is the center line will be called as delta J is equal to 0, the Rayleigh's line. Delta J is equal to minus 2 will be called as Stokes lines, and delta J is equal to plus 2 will be called as that is anti-Stokes lines. So here for the selection of diatomic molecules, delta J is equal to 0, plus or minus 2 is. So now for the equation, that is mu bar is equal to B into J into J into J plus 1. Now we shall write the equation for the Stokes lines, the anti-Stokes lines, and the next is the Rayleigh lines. That is equation number 1 is. Now the next one is called as equation number 2. It will be continued for that one. So that is what is called as delta nu bar is equal to B into J dash into J dash plus 1 minus of Bj into J plus 1. In the next step, the value of delta J is equal to plus 2. That is, the J dash minus J is equal to 2. We get J dash minus J is equal to, that is a 2 is there. In the next step, delta nu bar is equal to B into J plus 2 into J plus 3 minus of B into J plus 1. So in the next step, delta nu bar is equal to, so that is B into 4J plus 6. B into 4J plus 6, where J is equal to the 0, 1, 2, 3, etc. So now I can call it as, this is the equation number 3. This is the equation number 3, sir. And this is equation number 2. So that is mu bar is equal to the B into J dash plus 1 minus Bj into J plus 1. That is equation number 2 is there. Delta J is equal to plus 2. That is J dash minus J is equal to 2. We get it. That is delta mu bar is equal to B into J plus 2 into J plus 3 minus B into J plus 1 is. So that is delta nu bar is equal to B into 4J plus 6. If you simplify this one, that is you can get B into 4J plus 6, where the value of J is equal to 0, 1, 2, 3 is. Okay. So now we should continue for this one. Just a second. In the next step, delta J is equal to minus 2. That is J dash minus J is equal to minus 2. We get that is delta nu bar is equal to, that is B into J dash plus 1 minus of B into J dash plus 2 into J dash plus 3. J dash plus 3. In the next step, delta nu bar is equal to minus B into 4